Okay, I work on Atlas, and I work on Higgs measurements, in particular Higgs to WW. And so I'm going to be talking a bit about the interplay between experiment and theory in Higgs measurement. And the basic outline, I'm going to give you a really brief review of a couple of things that you should know about Higgs channels. Probably most of that you already know, but it's good to have it down. And then I'll start talking about the H to WW measurement in particular and how theory is related to it. In order to do that, I have to review how the measurement works. And then the big three issues that come up in actually doing the measurement that are related to this subject are determining that should say WW background modeling, the GGH signal modeling, and then the VBF background modeling. I guess I meant by this background to GGH analysis. And then the second part, I'll switch gears and I'll talk about interpreting the results you get from a variety of different measurements, talking about coupling fits, an aside on Higgs to invisible, and an advertisement on differential distributions that are going to be coming. Okay, so the first point on Higgs production is that there's several different methods to produce a Higgs in the LHC. You've probably all seen this graph before. I've put a little vertical line at the mass that we've found an object at. The dominant production is gluon fusion diagram, which is this. It has large QCD uncertainties, which I'll talk about for a few minutes. It's also interestingly sensitive to new physics in this loop if we could actually measure that rate accurately, which requires getting around the QCD uncertainties. The VBF production has small QCD uncertainties. It has this very distinctive signature because you get a forward and a backward jet due to the two quarks coming out of this diagram. And so that allows us to, one, get a more pure sample by tagging, and it gives us different access to couplings because the coupling here is directly related to just the vector boson couplings. You can have W's here, you can have Z's here. There's associated production, which is used only in special cases when you really have too much background problems. And predominantly, this is useful for H to BB, which I won't talk about in detail, but this is the guy that is dominantly used for H to BB because it allows you to suppress the background by tagging with this W or Z. Just enriches yourself in Higgs because the Higgs couples to heavy objects. And then TT bar H, which is more for the future, so I won't talk too much about it, but it allows you direct access to the top Yukawa coupling, and it's also another way that you can be tagging Higgsness because it's even more enriched in particles with strong Yukawa coupling. So if you want to tag the initial state to enrich your Higgsness of your sample, that's a way to go. Then, of course, your Higgs has to decay, and this is the plot of the branching fractions as a function of mass. As you all know, this is the special spot that we live at, which happens to mean that we have a lot of experimental access to a lot of the different couplings. Although many of them are experimentally challenging, this is the pie chart that shows the 125 breakdown of the branching fraction. And it's interesting to note that a very large part of this is difficult to access, right? So far we've seen WW, ZZ, and then gamma gamma actually lives in the little other slice. It's so tiny. So that just gives you a little bit of a sense of scale. We hope to see tau tau and BB sometime in the future. Some of these other guys are just hopeless or close to hopeless at a hadron collider. Okay, so I'm now just going to step through the three measurements where we've clearly seen a signal. I'm not going to talk anything about tau tau and BB. They're sort of on the edge of significance. It's not clear whether we're seeing a signal or not. It's still possible that when everything settles, there is no tau tau and BB as far as I'm concerned. Although I think at this point it's kind of unlikely. We see hints, but it's not enough to be certain that doesn't happen, that the end case is not that there's no tau tau and BB. So we should keep that in mind as a possibility, although unlikely. And so for the channels, one of the channels, so the reason I'm presenting these is to compare what WW looks like to what gamma gamma and ZZ look like. ZZ is famous for its low background, as people call it the golden channel. It has a nice signal to background of 1.5. You get a nice peak. But you get very few events. You can look at the size of these error bars. They're huge, right? So that tells you you're just not getting a lot of signal, right? If you go to gamma gamma, it's a different category. The gamma gamma signal is very small, but the background, and the background is very large, but you actually get good statistics. in the end, but the signal to background is over 1 in 30. So this is actually a very small bump here. And the way the background is done here actually doesn't involve theory at all. It really just takes this distribution, does a fit to it, and picks up essentially some sum of whatever the backgrounds are, and makes a nice, it's just a fourth order polynomial fit, and then you extrapolate under the peak and you calculate how much area you have to get your signal yield. So there's very little theory involved in this measurement. However, one of the large uncertainties is just in the shape of this fit line. You can vary the fit line, you can end up getting slightly different answers, and that ends up being a fairly significant variation in the measurement of the yield. So now we go into WW, which is the main point of this talk. It's intermediate between the two cases that I just talked about in terms of signal to background, with the signal to background of 1.8. It's challenging because there's no mass peak, because the only way to look for it is in the L nu final state. So you have two neutrinos, so you can't look and make a mass peak. You can make a very approximate mass peak. I'm going to use this plot to sort of guide you along into what the relative signal and background and contributions of the different backgrounds are as we go along. And what this plot is it's an approximate mass variable calculated like this. It's sort of the best you can do given that you're missing the invariant mass in the neutrino system entirely, and the z of the neutrino system entirely. Okay. So the reason that this has an interesting aspect in the interplay between theory and experiment is that there are many sources of uncertainty here. And so what this table is it's the uncertainties on the ratio of the measured cross-section times branching fraction to the standard model expectation. And what you see here, as I've highlighted in yellow, is that many of the systematic uncertainties, many of the uncertainties are theoretical. In fact, the first line here is just pure statistics. It's the statistical uncertainty. So that's still larger than the other backgrounds, other uncertainties. But when I sum up all these uncertainties, I also get about a 20% uncertainty. So you can say it this way, that the total uncertainty on the measurement is about half from systematics, many of which are coming from theory, and about half from statistics. So now you can imagine if I improve my statistics, this is going to be a problem because we're not going to get much better if it's already half systematics, right? And what are the biggest pieces here? The biggest pieces are the inclusive signal cross-section, the WW normalization, and then this object and Drell-Yan estimation. So that's basically an experimental question of how well is the correlation between when we cut on a particular energy or what efficiency we think we have for an object, how much we really have. And so we have all sorts of data-driven things to do that. These often go down or get better with data, with statistics, because as we get statistics, our controls that we use experimentally improve. So we get a better idea of what the actual energy scale of a jet is because we just have more jets to look at. And we can look at more specific scenarios and various things. So this can often get better with statistics, although it might get worse with pileup, as we'll have more pileup in the future. But that's going to get better. These other theory questions, they only get better not by adding more data, but by adding more thought, right? And so that's where we have to go. Okay, so why even bother with H to WW if we have ZZ and gamma gamma? As many of you probably know, it's not very easy within the range of reasonable theory to change the ratio of the H to WW to H to ZZ couplings. So we could just measure H to ZZ and assume H to WW is the same, and forget about WW. It's just too much of a mess. So that's one possible answer. Basically, this statement is coming from precision electroweak measurements. It's probably pretty close to true, although I'm sure that somebody out there can come up with a way to break that ratio. But the other thing to keep in mind is that even with all the mess that I just described to you, with all that table of uncertainties, and that's actually a condensed table of uncertainties, the uncertainty on the WW is better than ZZ. Remember, this is half theory already, or half systematics. So if I really think about this, it is 20% uncertainty for WW compared to a 30 or 40% uncertainty on ZZ. And so ZZ has much worse statistical precision, and there's not much you can do about that. So you take more data, you'll get better precision, but you're up against a brick wall, whereas this one is going to get better, but only if you can keep the theory under control. Okay, and so this is just a table to give you a sense of the relative sizes of the uncertainties with the amount of data that we have now, although these two guys have slightly less than the full data set, so these will get a little bit smaller. Okay, so I want to make a comment on how these things scale as we go up at higher in energy. So if we go up in energy, the LHC plans to run at 13 or 14 TeV for the next 15 years. This is the kind of program that we expect. 2015 to 2016, we expect 100 inverse femtobarns of 13 TeV data. So that's roughly 4 times the amount of data we have now, but all the cross sections go up as we increase the energy. So they go up between a factor of 2 to 2.6, or for TT bar H, it goes up even more, up almost a factor of 5. So you will get more cross section for a variety of the Higgs processes, and very nicely the signals tend to get larger faster than the backgrounds. So that's a nice feature. So you expect something of order 10 times more signal in this 100 inverse femtobarn sample than we have now, basically just using the scaling of the cross-section and using the scaling of the luminosity, and about 8 times more background. So you gained a little bit in signal to background, but 10 times more gives you a sense of where we're going in terms of, if I take that uncertainty where I had 20% from systematics and 20% from statistics, and my statistics is now 7%, well then I have to figure out something to do about my systematics. Okay, so the HWW analysis consists of looking for 2 main different channels here. What we do is we look in the two leptons, either of which can be E or mu, and 2 neutrinos. The processes look like this. There's the gluon fusion with the W's and then your 2 leptons, the vector boson fusion, which gives you 2 leptons, 2 neutrinos, and 2 jets. But you also get 1 jet from the gluon fusion because you can just radiate a gluon off of this guy and get an additional jet. And this happens with a fairly high rate. I think it's about 30% of the events with our 25 GeV cut have an additional jet. The other thing I want to say about this is that really this is a story about how to dig out a background, a signal under a relatively large background when you don't have any peaks. And that kind of lesson will apply to lots of other searches that you might be thinking about. So you might want to think about the concepts I'm going to talk about with control regions and how they extrapolate into signal regions as something you might do, for instance, to look for what Patrick was talking about, where there might be a WW signal for a dilepton plus missing energy signal for new physics sitting right under the WW. Well, these are the kinds of things that you have to do that I'm going to describe in the next couple of minutes to try to find those. Okay, so what are we digging them out underneath of is this giant pile of stuff. Patrick introduced this last time. This is actually a newer version of the plot. The only real difference is that now there's measurements for 7 TeV and 8 TeV for a fair number of the processes as you go along. Again, this covers several orders of magnitude. This is 4 orders of magnitude coming across here. And it's actually worse than that because these guys don't have their leptonic branching fractions in them, so they're actually lower than that. And so what we're looking for is this thing that's underneath. It's an order of magnitude below something that is already 3 or 4 orders of magnitude below the biggest backgrounds. So you need a lot of background suppression. And so what I'm going to do is I'm going to talk for the next couple of minutes about how you deal with all these various backgrounds. And the important one that's going to come to a head is the WW one. Okay, so if we start with the W jets background, basically this we use lepton identification. I'm not going to go into a long story about this. When I find a lepton, either a muon, which is in the muon chambers, I look and veto there being energy around it that would indicate that it was actually a muon inside a jet. I can do something similar for an electron, and that will suppress the things that look like electrons or muons. Sometimes they're actually real electrons or muons from heavy flavor decays. That will suppress those in favor of things that actually came directly from W's. So this background is actually quite small on the plot. That's the light blue area down here. But the problem is it's very difficult to determine because this is the tail of the fragmentation of a jet. So this guy's 3 orders of magnitude up from our signal, right? And the way we got rid of it was making a cut that actually gets rid of 4 orders of magnitude of it, because you can now see that it's small. It's 3 orders of magnitude up from the WW. It's 4 orders of magnitude from the Higgs. So we had to make a cut that was 4 orders of magnitude, and that's 4 orders of magnitude that's sort of looking into a corner of jet substructure phase space, right? So that means that it's not easy to determine. There's no way we're going to trust a Monte Carlo to do this for us. So instead, we calibrate it with data. But there's still all sorts of uncertainties in extrapolating from one sample of data where we measure that 4-order magnitude suppression rate and where we apply it to. And that ends up giving us about a 40% uncertainty on that little light blue area. So that ends up being one of our larger experimental systematic uncertainties. And it's something that I think with more data with more data, we will probably be able to do better. Although, in fact, the 40% uncertainty that we have there comes from our limited ability to test our procedure for calibration and data using Monte Carlo. We can't generate enough Monte Carlo to actually make a good test. So it's actually a computational limit that we've hit. And so there's probably clever ways around that we're working on for the next round. OK, the next background is Z plus jets. And what Z plus jets is basically I have 2 leptons, and there shouldn't be any missing energy in a Z plus jets event, but I have experimental resolution. And what happens is that there's 2 different categories. We have to divide our thinking about this into 2 categories. The E mu category, in the E mu category, I don't get Z to EE or Z to mu mu as a background, but I instead get Z to tau tau, where 1 tau goes to E and 1 tau goes to mu. And there, if I make a reasonably smart cut about the size and direction of the missing energy signature, I can get rid of the background almost entirely. So this guy's pretty robust. It's not a big problem. But if I want to look at the same flavor category, EE and mu mu, it's much more difficult. And what ends up happening is that you have to make a lot of stringent requirements to get rid of this background. Jesse, during his talk just a few minutes ago, wanted to know how bad pileup is for missing energy. And the answer is it's so bad that for it took us basically a year to figure out how to dig the signal out from the pileup. So in 2011, we had relatively low pileup, and we used all of these E mu and EE and mu mu together. The analyses for the 2 different categories were almost the same. When we quadrupled the pileup, when we went to, actually, let me see. So I'm going to skip out of order here for a second. This is what the pileup looks like, just to show, and I wanted to show this plot. This is 2011. Here, the amount of pileup that we had in 2011, and you can see it's relatively low. And then you look in 2012, and the pileup is up here around 20. So to give you a sense of what that looks like is you've got this C here of collisions. This is the Z along the beam direction. There's actual collisions. This is actually a Z to mu mu event. So here's a Z to mu mu, and here's all the other random minimum bias collisions underneath there. And so the energy from all of these just dumps in the calorimeter, and we have limited resolution, and that smears things out very badly. And so we can't actually just cut on missing energy anymore. Instead, what we have to do is we use something called track missing energy, which is just summing up the tracks from the vertex. So now I can actually look and take a particular vertex where I see 2 leptons coming out, and I can take all the tracks from that one vertex, and I can make a missing energy. But of course, I've lost all the neutrals now because I only see the charged particles. So that gives us some measure that helps us suppress the background from Z to plus jets again. And then the other thing that we can do is we can actually look, if I have 2 muons like this, I can look for little small jets coming off the other side, small enough like between 10 and 25 GeV. So because we've already vetoed out the larger jets, I'll tell you a little bit more about that in a minute, we can look for little jets coming out the other side, recoiling against it. And we have to calibrate that again with data because we can't rely on the theory to do that for us at this point. And particularly also, we can't rely on our detector calibration to do that either. We have trouble calibrating jets below 25 GeV in addition to the theory trouble calculating them. OK, so coming back here, so this plot is made after the strange requirements of the track missing ET that I just described and these little soft jets. And you can see even after I've applied all these extra cuts, I still have a fairly significant background. It's comparable in size to the Higgs signal, right? So it's a difficult process to look for these EE and mu mu. And in the end, this only contributes a fairly small amount of our sensitivity. I think it's about 10% of our sensitivity. So it's almost all coming from this plot. And I suspect that in the future, unless we suddenly get much smarter about how to suppress pileup in the missing energy calculation, we're going to have to jettison this half of the analysis. It just won't be worth it after a while. Okay, so just to describe what the missing energy is, I think everybody probably has heard this before, but what we do is we just take a sum over all the calorimeter cells. For each cell, we can associate a PT with it, although it's actually an energy measurement, which is why we call it missing energy. But we just take the direction of each calorimeter cell, and we can sum over them, associating, essentially thinking of each calorimeter cell as being a massless particle with a particular energy, and we get out this missing ET variable. And what we actually end up doing is inventing this funny variable called missing ET rel, where if the missing ET is away from the two leptons, so if I have two leptons going off like this, and I have the missing ET over here, I count the full value of the missing energy. But if I have the two leptons like this and the missing energy is in this direction along the two leptons, then I only count the part that's transverse to the two leptons. And the reason that that's actually very useful is because if these two leptons were actually taus, and so I have an E and a mu, but they came from taus, then the neutrinos are both in that direction. I tend to get the missing energy in that direction. And so this sort of makes a smooth transition from things that do not look like zeta tau tau to suppressing things that do look like zeta tau tau. I actually invented this variable way back on CDF because our calorimeter had a tendency to lose energy because it had a lot of cracks in it. So that's not so much a problem with CMS and Atlas, but because it still works well for zeta tau tau, both experiments are still using that variable. Okay. So I talked about that. Okay. So, how do we model the pileup when we do these measurements? Because now I've made this cut on missing energy. I can calibrate how much Z plus jets I get from various data-driven procedures, but I also have to know how this affects the resolution on the WW signal, and that I usually use a Monte Carlo for, but how much do I trust that? And so I want to make a comment that one place that we're using theory that you might not have thought about, or tuned Monte Carlos more than theory, is to model the properties of the pileup Monte Carlo, the pileup. And so the pileup is soft QCD. Its properties are fairly hard to model, and what ends up happening is we tune them to various measurements. And so this is an example of a measurement that it gets tuned to, which is just the number of charged particles per unit rapidity as a function of the PT, per unit rapidity and per unit of PT. And you can see these various following distributions. It looks pretty nice in this plot on a log scale that covers 10 orders of magnitude. But if you make a ratio plot, you see that some of these tunes, the red and blue tune, are the tunes that we used early in 2009 and 10, and early 11 actually. And then the purple is the tune that we use now. And it still actually turns out to not be that good because this plot doesn't actually capture all of the functionality. You have to, basically, if you did this plot in every regime of eta, every range of how far forward in the detector you would get different distributions, and the Monte Carlos don't fully reproduce all of those. So you get these discrepancies, and what we find is that if we look at a distribution like the missing energy distribution, and we look at it as a function of the pileup, we see increasingly bad agreement as the pileup goes up, and that is basically just a question of how well we are modeling in our Monte Carlo the properties of the minimum bias collisions. Okay. The other thing in these events, as was mentioned earlier, is these underlying event, which is that you've got these two protons. They've collided. You can see this is actually a Tevatron diagram. They've collided, and you get the rest of the protons coming through. There can be additional multi-parton interactions here where you have an additional pair of partons colliding. You can get other effects like ISR, where you draw some line between when it's hard and when it's not, and some of that counts as underlying event. So you get these other effects that produce soft QCD going on, and those have to be modeled both for the signal and for all the backgrounds, and that contributes additionally to the quality of our modeling. Okay, so now we're moving along. We've gotten rid of Drell-Yan and the W background. These are sort of reducible backgrounds. I can cut harder, I can get rid of them. Now I get to the next category, which is top. And so there's actually three kinds of top that we should be thinking about. TT bar, where I think you all know the diagram, I didn't put it down here. Single top, which counts as these two diagrams. And then there's another flavor of single top, which looks like this. And this guy is actually the worst one. And the reason this guy's the worst one is because it has two real W's, one that's going to come from the top decay and one that comes directly from the hard interaction. And then you get, so that means you have two real W's, and you only get one B jet here because this B jet tends to go down the beam line. This guy is really, you can think about this as a gluon splitting into two B quarks, and one of them getting knocked into the detector and the other one going down the beam line. So this guy tends to get lost, which only leaves you two W's and a single B, which means that you only have one jet in the event. TT bar has two jets in the event, and what you're going to do is you're going to try to get rid of or separate out the backgrounds based on how many jets they have. The problem is, of course, you can also get jets radiated in the gluon fusion diagram, so you can't just require there to be no jets because that's going to kill some of your signal. So what you end up doing is slicing and dicing. Instead of actually cutting out this data, we separate the analysis into three pieces. We have a zero jet piece, and there's no, the Higgs is not actually very visible here, but the Higgs distribution looks fairly much like the WW distribution, which is the dark blue. It's a little bit more prone to giving you one jet than the WW actually, because it's a glue-glue instead of a QQ bar collision. So we divide the analysis into zero jet, one jet, two jet. Most of the sensitivity right now comes from zero jets. One jet we do include. We use B tagging to veto out, make sure that one jet is not likely to be a B jet. That gives us some reasonable separation. I'm going to sort of not talk much about one jet because it's not as interesting. It's not as sensitive as the zero jet, and then the two jet is specialized to VBF signature, which is the only way you can deal with this giant top background that you see here, the yellow area. So that's interesting because you can get rid of the top by looking for the specialized vector boson fusion scenario. Otherwise, it probably wouldn't be an interesting thing to try to deal with. OK, so then we've sort of somehow dealt with the top background. In the zero jet, you can think of it as reasonably well suppressed. And we're left with probably the biggest background, which is the WW, which is an irreducible background, meaning that there's no detector level cut that I can use to discriminate these things. All I have is kinematics, essentially. But it can be partially suppressed using two different kinematic things. One is the effect of the spin correlations, which I'll describe on the next slide, just to make sure everybody knows that story, and this approximate mass variable that I mentioned before. And so what we need to do, remember our signal is way down an order of magnitude below this background. OK, so the way that the kinematic suppression using the angular correlations works is that we start with a Higgs. The Higgs is going to decay into two W's. Well, in order to have a spin 0 for the Higgs, the two W's, the spins have to be opposite directions, right? And so if the two W's have spins opposite directions, and then they each decay, they're going to decay into two fermions. In order to have the spins add up for the two fermions, they have to point the same direction, right? So if I want spin 1/2 to add up to a spin 1, it has to be like that, spin same the other way. And if I look at this, well, for the W plus, if I want this to decay to this has to decay to a positron and a neutrino, and so I know the neutrino has to be left-handed, so that means this guy has to be the neutrino, and this guy has to be the positron, which is a right-handed, for its coupling to the W. And so just by the fact of the kinematics here, I know that the two charged leptons have to go the same direction, and the two neutrinos have to go the other direction. And that means that the angles between them are going to be small. And so that has two observable consequences in the detector. The first is that the angle between the two charged leptons is small, but then also the invariant mass of the two charged leptons is small. The other thing to keep in mind is that now that we're looking at 125 GeV, one of these W's is off shell, and that means that its invariant mass is going to be small, right? And so that tends to also make the MLL small. So that further suppresses the MLL. Okay. So here's what these distributions look like. This is the MLL distribution. And here you can see the blue is the WW background, which is our irreducible. So we've done a reasonable job at getting rid of everything else. By the way, if these guys were much smaller than the blue, then you would know we'd cut too tight. Because basically we want to cut to the point where these guys are comparable or slightly smaller than the irreducible ones. Because otherwise we're just burning efficiency because we're not gaining anything by getting rid of these guys at this point. This guy is the dominant issue. And so here's the MLL distribution. Here's the delta phi distribution. You can actually see in MLL, it's kind of a pretty good discrimination. The red is really only below 50 GeV, and the blue keeps going up to 250 GeV. In delta phi, which is the famous variable, it's quite different. The other thing I want to point out is that this guy that drops off over here, that's actually not a physical effect. That's an effect because we make a cut on the PT of the two lepton system, which is effectively highly correlated with delta phi LL, and so that sculpts this distribution down. One thing that I have yet to understand, and maybe everybody here wants to think about, you can look over here on the edge of this plot. Every single data point on this edge is below the line. We don't really know why that is, and CMS's plot looks pretty much the same. So there's definitely some kind of, this is a region where you're sensitive to the soft QCD, the soft boost, the PT of the WW system. And so somehow we're not doing very well on the soft end of the PT of the WW system. So I don't quite know what that is. We've spent many, many hours debating that as we try to go through and confirm that we understand enough to claim our observation of a signal. Okay, so the approximate mass calculation, I mentioned this before. We do this basically, if you just take a mass calculation, you just drop out of the calculation. Everything you don't know, that's the closest you can do. It has the right basic kinematics that the transverse mass, as defined there, is always less than mh, which is good. Because it means that I can now look. This is all missing energy resolution, so there should be a hard cutoff at 125, and the fact that the signal tails up a little bit, that's the resolution on this ET miss in here. So that's good that it's a reasonably well-defined thing, but you'll notice that it's about almost as broad as the background distribution, and where the background distribution, almost all these blue guys come from things with 2 on-shell Ws, which means they have a mass of at least 160. They're probably typically around 200 GeV true invariant mass. So your discrimination is not spectacular here. In the end, what we do is we take this distribution and fit it. So we've made all these other cuts and selections, and then we finally take this distribution and we fit it because that's the closest we can get to signal. And that just makes the most use of the fact that different bins in this distribution have different signal-to-background ratios. Okay. Okay, so the final set of backgrounds are these are things that we call other diboson backgrounds. They're WZ, where usually WZ background comes in from having a W and a Z to LL. So you have 3 leptons, but you lost a lepton. You can also get background from QQ bar goes to Z gamma star. The gamma star goes to LL, and the Z goes to nu. This is actually a fairly small background, but it's something that we have to include. These are generally modeled with Monte Carlo. There's one special background that doesn't go on this, this famous plot, and that one special background is W gamma star. And Sunil referred to this on Monday. It's a category where this gamma star can be nearly massless. And so you can have a W that goes one direction, decays to a lepton neutrino. A gamma star going the other direction, decays to 2 leptons. But if you lose one of those 2 leptons, now you have something that looks like 2 leptons and missing energy. And so it's very easy to lose one of those 2 leptons if they're nearly collinear, and you can get an asymmetric conversion that puts most of the energy into one of these 2 guys. It's not actually a conversion because it's happening in the hard interaction. And the problem is that these are difficult because most Monte Carlos are not tuned to deal with the fact that there's a pole right at 0 here. And so you end up getting very large weights in your next, like if you run an NLO calculation in a simulation, you just get a very large weight because of the pull from the gamma star. Okay, so we've talked about where the WW background comes from, that it's irreducible. Well, how do we deal with it, right? Well, we deal with it by knowing what the actual magnitude of it is underneath the signal. In order to do that, we need to get underneath the signal, but the problem is that we've made these jet requirements. This is a zero jet distribution, right? There's no jets allowed in these events. And when we made that cut, we've actually introduced a dependence on on a new scale, which is the scale of the cut, and that makes it difficult to calculate the actual WW to zero jet cross-section. So QQ bar to WW plus no jets is not easy to calculate. Certainly, so how well do we need to know it? Well, we need to know it. I can take the signal to background, which is 1 over 8, and I can multiply that by the 20% that's the expected statistical error. And if I multiply those together, I get that I need to know to 2.5% the amount of WW. In other words, I need to know the area of this little triangle here of dark blue to 2.5%. Otherwise, I can't capitalize on the statistics of getting the 20% uncertainty that I can get on this red area. So that's a small number. As it turns out, right now in our document, we claim that we're doing this to 1.6%. And the way we get that is by using control regions. And so the control regions look like this, that what I do is I divide my data up. I have this MLL distribution, and I say, okay, I'm going to take the data in this region, and I'm not going to try to calculate how much shows up in this triangle. I'm going to calculate the ratio of this area to this area. And when I do that, I expect there to be much less uncertainty, because now the jet uncertainties that came in when I made this jet requirement aren't very different between here and here, and so they cancel the first order. And so we use a Monte Carlo, MCFM in particular, to calculate the effect of this veto and how well we know that. And so here is a set of uncertainties that we assign to that extrapolation. I should have mentioned back here that the signal region, we actually divide it into 2 slices, one for the first 2 bins and one for the second 2 bins. And that's just because these 2 bins have better signal to background than these 2 bins. So that helps the situation a little bit. And I'll just show you a table for the extrapolation from this area into the first 2 bins, just as an example. So how do we get this uncertainty on this ratio? Well, we get the uncertainty by varying the factorization and renormalization scales. I'll explain that a little bit more in the next slide. That gives us about 1%. Varying the PDFs, that gives us 1.5%. Then there's the underlying event and varying parton shower models. Underlying event has various ad hoc models that are tuned to the data, including multi-parton interactions and such. It seems to not make a very big difference. It turns out for the 30 to 50, it makes a bigger difference. I'm not exactly sure why. And then there's something we call modeling. And modeling is really just, we have multiple generators. The people who wrote the different generators have made different extrapolations or estimates. And so we assign as an uncertainty the difference between these guys. And typical differences come in from things like whether or not one generator may have assumed massless B quarks and another generator didn't, things like that. They can introduce small differences in the modeling, but you can see that they're non-trivial in the actual effect. Okay, so let me just say why people vary normalization scale, renormalization, and factorization scales. I've stolen this slide from Mangano, so you should have seen this already. When I calculate a cross-section, I integrate over the PDFs, and I take the partonic cross-section, I integrate over the PDFs, and I integrate over the parton shower to get an actual prediction for a process. If I did this to all orders, it wouldn't matter where I factorized what was in the PDF and what was in the hard scattering and what was in the parton shower, but I don't do this to all orders. So by varying these things, I'm getting a rough estimate of what the uncalculated terms are. And so that's the idea behind that variation, and it's a very common procedure. As an example of how that works, I'll give you the GGH signal. And so for the GGH signal, this is actually the single largest uncertainty on the observed signal strength, because we're dividing by the standard model cross-section when we reported signal strength. And so it's actually the uncertainty not on what we observed, but on the uncertainty on that denominator that dominates the systematic uncertainties. And so here is that cross-section that we're dividing by and a leading order calculation. And you can see there's a very strong dependence on the renormalization and factorization scale. So here they varied them together. They just tied them together and varied them both at once. And so typically people go from half the Higgs mass up to the Higgs mass. And so you're going in this range. You see if you used a leading order calculation, you get a big discrepancy. Next to leading order, somewhat less. And NNLO, and you're starting to get pretty flat, although it still has a shape. And you end up with, from this basic procedure, giving you a 7% uncertainty on that quantity. Okay, so a couple slides now on the next biggest uncertainty. So I just said that the biggest uncertainty is from the theory side is what we divided by. So there's another uncertainty for the signal acceptance, which is how much did the I'm measuring in zero jet. So what I'm measuring is how much Higgs is produced with no jets, right? But I don't actually want to know that. I actually want to know how much Higgs is produced from the gluon fusion process. I know that the no jets is dominantly coming from gluon fusion, but I don't know how to relate Higgs plus no jets to gluon fusion precisely. And so the way you do this is you have to make a calculation, and that calculation has a large uncertainty. So I'm just going to describe an interesting note on the theory side about some work done by Stewart and Tachman about realizing that basically everybody had underestimated the uncertainty on that extrapolation. So the thing is that GGH is full of gluons, which means you get lots of strong interactions, lots of jets coming out, and the jet cuts make it significantly harder to calculate. So what you have is this inclusive cross-section looks like this. There's a series in alpha S. But when you add a cut, you're adding in these logarithms in here, the ratio of the cut to the Higgs mass in there. And so really what the calculation looks like for one jet is alpha S times a series of logarithms. You guys all probably know this better than I do, but I need to explain this in order to make the next slide make any sense. And where L here is the logarithm that you have. So you get this series. Now, in addition to alpha S, you have all these logarithms. And what you want to do, if I want zero jet, I need to subtract. I need to take this total and subtract this guy with all the logarithms, right? That's how I get the zero jet. So I do that subtraction. Here's the inclusive cross-section. Here's all those logarithms. Turns out because of the minus sign here, that these guys actually tend to cancel. These corrections to the Born cross-section, they're canceling out. And that causes a problem because they're only canceling not for any deep reason. And so they may not cancel at the next order, the order you didn't calculate. So if I just vary renormalization, factorization, and think, oh, I'm varying these things that I didn't calculate, well, that sum, I'm only seeing the part that I calculated where I know there's a cancellation, but I don't know there's a cancellation in the next order. And so what they've shown here is a plot of the cross-section as a function of the cut. And what you can see is that there's three different, there's a blue line, which is using the normalization scale mh/2, a dotted green line, which is using mh, and a dashed green line, which is using mh/4. And what you see is that they have slightly different dependences on the cut, but at the cut value that we tend to use in experiments, which is in this range, they all agree. But that's just a coincidence. It's a cancellation between these terms with alpha s's and these terms with logs that doesn't have to happen at the next order that you didn't calculate. And so that introduces a significant uncertainty. And so what Stewart and Tachman have said is, look, what I should do is I should just assume that the inclusive cross-section, which is these terms, and these terms are uncorrelated. And then the uncertainty on them is uncorrelated. And if I assume the uncertainties on them are uncorrelated, I can get an envelope that I actually believe will cover and won't be artificially small because of just cancellations that are arbitrary. And so they end up telling you you should use this green envelope here. And the end result is that green envelope is big, right? So that means that we have large uncertainties, and that ends up in our table as one of the dominant uncertainties on the measurement. Okay, So that's the end of that. The next topic is VBF. So in VBF, we want to look for this because we get different sets of couplings in the collision. And we can start using these forward and backward jets as taggers. And so how does that work? Well, here's the rapidity distribution for a jet in one of these events. The black is the rapidity distribution of the VBF process. You can see they tend to be forward or backward, whereas something like TT bar, which is one of the biggest backgrounds, by far the biggest background, is very central. But of course, it's broad, and I'm looking for a signal. This black line is times 2,000, right? So I'm looking for a very small bit of signal, and you can see that even though this got the yellow area here is very central, it's got tails that go well out here, and they're not 1 in 2,000 over here. The variables that we end up using are delta yjj, which is the rapidity difference between the two jets. So basically requiring them to be like this, very far apart. Again, here now we're down, once we start looking at this, of having this black line is only times 50 now. And the back line actually includes two different processes. It includes VBF, which tends to be over here, and it includes the associated production, which tends to be over here. So if you're wondering why there's a little bit of a rise in the middle, that's due to the VH, whereas the VBF is definitely peaking in the forward region. And you can also look at the invariant mass between the two jets. And by the time you make these two cuts, you actually get a very clean signal. You get a signal to background that is close to 1-to-1. It's a little bit worse than 1-to-1. The pink area here is the signal. The red area is background that you get from gluon fusion plus two jets. So you just get something that looks like that, where you've just radiated two jets. These jets can also be fairly forward-backward. It's not easy to understand that background. And by just doing the usual renormalization and factorization scale variations, we end up, and varying the PDFs, we end up with uncertainties that are in the 40% range for the contribution of this guy, which is this red area here, to that plot. And now, of course, the signal of yesterday, which was we found the Higgs in gluon fusion, is now a background because we want to see the Higgs in VBF, right? The W plus jets background, which is over here, also has a large uncertainty, basically from the same kind of issue that you get. You can get two gluon emissions from the various, and there's a whole series of diagrams, it's a fairly long series, in addition to your WW from the standard T-channel process. The TT bar also has a significant background. We have an advantage with the TT bar, which is that if one of those jets is in the central part of the tracker, so between eta of 2.5 plus or minus 2.5, we can look and we can make a B tag instead of a B veto. And if we do that, then we'll be able to count, we'll have a very close cross-check, right? We have a control region that's very close to our signal. The only difference is one, the detector managed to identify the B, the other one that didn't, and we have fairly good control over that ratio experimentally, so we actually get a reasonably small uncertainty on that guy of 15%, although it's interesting you see very few data points in here, but now think about what this plot's going to look like in 2022 or in 2028 when this guy has 1,000 times more data, right? It's going to be a spectacular thing to look at. It'll be very precise if we can control what all this stuff is in here. You'll notice that all those histograms are kind of bumpy, and that's because we have trouble generating the Monte Carlos in these regions because of you have to simulate a very small corner of phase space. We tend to want to generate an inclusive simulation, and then if we look at the small corner of phase space, we just run out of statistics. So one of the things that we have to work on is our ability to generate simulations that are specialized to these corners of phase space. I think that one will have well under control by the next round of data taking. Okay, so just as an intermission, this is a Higgs to WW event in the vector boson fusion channel. This is probably one of the most likely to be an actual Higgs events that you've ever seen an event display for. The invariant mass of these two jets is up there in the 2 TeV range, which means it's very, very VBF-like. It's almost certainly some kind of VBF process. I should have mentioned back here that in addition to the W plus 2 jets channels that look like this, we also get WW where it's an actual VBF process. So it looks like the VBF diagram where two W's come in, they scatter off each other, and they go out. And so when I look at this event display, I'm pretty sure that that's got to be a VBF process. The invariant mass of those two jets is huge, right? Very small chance of being anything else. And then I see an electron going one direction, a muon going a very close angle together, and then missing energy going the third direction. There's very few processes that do this. This is very likely to be a Higgs event. Okay, so that's the end of my WW story, and I come to the last set of things that I wanted to talk about, which is, okay, now I've done this measurement. I've done a bunch of other measurements that you've heard about, gamma, gamma, ZZ. We're close to having BB and tau, tau, right? We hope to see those soon, or be able to say they're not there if they're not there, or suppressed if they're suppressed. So we've got all these different things. What we end up doing to interpret them, because what we want to do is work backwards towards what can the couplings be and are they the standard model, is we take these and we put them in a combined fit, and we can get out coupling constants. We can also put in kinematics into our combined fits and get out properties and quantum numbers. I'm not going to talk much about that unless we happen to have time at the end. I should mention now that maybe I should pause for a second and see if anybody wanted to ask questions on the WW discussion. Yeah?
Patrick was telling us yesterday that the WW measurement itself is somehow off in CMS and also in earlier Atlas releases.
Mm-hmm.
And you've not seen quite right here. Is this because of the data-driven analysis? Or
yes. So this is a good question, so let me repeat the question. If I go back, where did I put that? There it is. Okay. So the question is that this plot looks good. There's no obvious normalization issues here. Yet, when you do the inclusive WW cross-section, you get a slight difference in the 2011 data, and CMS sees it in both 2011 and 2012. You just get a slight enhancement in the WW cross-section. And so the thing is that this is a data-driven plot. This is the control region. And so this plot is actually normalized so that this region in the control region agrees. And I can actually tell you, because the numbers are in the paper, that this is about, we had to scale up the blue by about 10%. Now that's another important point that Patrick was making the other day, which is if that 10% is new physics and not just some soft QCD that's, you know, the next to next to leading order piece that wasn't calculated, something like that, then there's no guarantee that we're getting the ratio of our control region to our signal region right. I would not feel so bad if I got the Higgs cross-section wrong because of new physics, but we would like to know if the new physics is there. So that would want us to continue to look at distributions like this, and maybe if you wanted to do a new physics search, you would redefine the control regions and call this and this control regions and look in here, right? Something like that. I think that, you know, Patrick was pointing out that it's this region in general that tends to have the discrepancy. Another interesting point along this lines is that last year and up till HCP, which is in November, we defined our control region to be from 80 up. So we defined this to be our control region in here. And that actually significantly increased the extrapolation uncertainty. So instead of this being 1.6%, it was 4%. And that was the limit on the measurement at the time. So redefining the control region from this to this actually reduced the uncertainty significantly. Okay. Other questions? Yeah.
I think you said for Higgs to WW, you explained why the electron and muon angle between them tend to be small.
Mm-hmm.
Can you restate that?
Sure. So yeah, this is, okay. So it looks like this, that I have a Higgs spin, which is 0. The Higgs decays to two W's. They both have spin 1. So the only way that they can add up to 0 is if one has a spin one way, the other one has a spin the other way, right? And then those guys decay to two fermions. The black lines here are indicating the momentum direction, and the blue lines are indicating the spins. And so they have to go opposite directions. And I've chosen the spin to be along these axes. The fact that you can also get the spin along this direction just smears out the effect. It doesn't eliminate it. So the effect is that now this spin 1/2 and this spin 1/2 have to add up to the spin 1. So there's the only way I could have written that down, right? And so now I know if this guy's moving this direction and its spin is this direction, it's a right-handed particle. If this guy a W plus is decaying to a positron and a neutrino, the right-handed particle among positron and neutrino is the positron. And the left-handed particle is the neutrino. If I go over to the W minus, then I get the same thing. This guy has to be left-handed. Well, the left-handed particle in this W minus decaying to mu minus and an antineutrino is the mu minus. So the mu minus has to be this guy, and the neutrino has to be this guy. So now you see that these two guys are going the same direction. And you get this spin correlation. That's really the crux of how you actually see the signal. It's why the MLL is small, and it's why the delta phi LL is small. So yeah, so that's the assignment that you get, and there's the consequences. And it's what allows you to do the control region thing as well. This was much more difficult. We actually relaxed these selections to look for spin 2 because people had to be sure that it was spin 0. I always kind of knew, and I wasn't very excited about this because we wouldn't have even seen the Higgs in WW if it was spin 2. It would have been a massive coincidence because the rate would have had to have been like if I had a graviton, I would have to enhance the rate in WW to compensate for the fact that the efficiency was lower for WW than it was for ZZ. And so you would have had to have a very special model to fake a Higgs. It would have had to had a funny ratio of WW to ZZ just to end up looking the same. Okay. So any other questions on that? Okay. So so now what we want to do is we want to take the variety of measurements and we want to combine them and try to extract as much information about the actual underlying theory as possible. And why should and so this story is partly about why experimentalists have to be deeply involved in this, although I won't go into too much detail about that. So just to remind you here, the production mechanisms, right? I already showed you this slide. They have different accesses to different Yukawa couplings in here. And so that's one of the motivations is we want to tease out what these actual couplings are in these guys. And so when I make a plot for the Higgs signal, and I showed you this plot before, this doesn't actually tell you anything about the production mechanism. I only tell you about the decay mechanism. I have gamma gamma, and I haven't made any selections in this plot that differentiate the different production mechanisms. But actually what we're doing now is much more complex. So now what they do for the gamma gamma channel, I'm not directly involved in gamma gamma, is they have a whole flow of selections that separate out and enrich different subsets in different categories of production. And so the way this works is you start with the diphoton sample, which is everything in the plot I just showed you, and you say, well, if there's an additional lepton in the event, then it's probably a WH or ZH event. So I'll put that in a category for having one lepton. If there's evidence of missing energy, then it's probably also a WH or ZH event. So I'll put it in the missing energy category. Then I'll say, okay, if there's two jets, but they're low mass, so they're not high enough mass to be a VBF, then they're probably WH or ZH where the W or Z went to jets. And so now I have another category for that. And then finally, I get down, well, now I have two jets, but these two jets are too high mass to be from associated production. Maybe they're from VBF. And so I have two different selections for VBF, a type 1, which has a loose one that has a 54% fraction in that sample of VBF. So that's 54% of the Higgs in the loose sample is VBF, and 76% of the Higgs in the tight sample is VBF. And the remainder is basically GGF. I actually should have been reading these numbers as I went along. In the single lepton, it's almost all actually WH or ZH with a tiny bit of TTH in there. In the two-jet bin, it's about half WH and ZH, and the remainder just GGF, where you just happen to have two light jets in the right places, two jets with a relatively low invariant mass. And then finally, I get down, after I've removed the WH categories and the VBF categories, I get down to what's essentially all GGF. This is 95% of the signal Higgs that we actually get. And we divide it now into various detector-dependent categories based on whether the photons converted or not, whether they went to regions of the detector with higher or lower resolution, et cetera, things like that. And it actually divides on the PT of the gamma-gamma system, which has a little bit of sensitivity to VBF versus gluon fusion, which is why the GGF fraction varies within these categories by a little bit, because the higher PT ones tend to have a bit more vector boson fusion contribution. And so for each one of those categories, I can now do a fit that looks like the fit, that looks like this fit, except that it has much less data in it because I've now subdivided the data into lots of little bins. And each one of those, I get a yield. And so this is the yield for each one of those bins. And I get the grand combination down here, doing a statistical combination. You can see that none of these bins really have a clear signal. But if I add them all up, I know the signal's there. So now I'm relying on statistics. I've divided things up into many categories where it's no longer a clear signal, but each one of those categories has information in it. And I can put those into grand fits. And so the first grand fit you do is don't even think about the other physics decay channels. Just focus on gamma gamma. I can just divide the observable that I want to extract from this fit. I put all these different categories in. The observable that I might want to extract is one observable, which is I can rescale the strength of the VBF and VH signals relative to the strength of the GGF and TT bar H signals. And the reason that you would want to do that is because the VBF and associated production are proportional to boson couplings, Higgs to boson couplings, whereas TTH and GLU-GLU-H are proportional to top couplings in the standard model. And so you can think about this a little bit as being the fermion or top coupling versus the boson coupling. And now you have a likelihood where as I change those two parameters, sometimes I'll get values that just disagree with the data, and sometimes I'll get values that agree with the data. And I can plot out the likelihood distribution here and make little error ellipses. So 68% confidence level is that the true value lies within that little circle there. At 95%, it's here. You'll notice that gamma gamma, everybody has heard that it's enhanced in Atlas, and it was enhanced in CMS until it wasn't. And this is the standard model, so you can see it's about 2 sigma out in that distribution. And it's not that it's 2 sigma in one parameter or the other. It's sort of diagonally off. Okay. This is more of an advertisement plot, but I think it's interesting and a little terrifying at the same time. This is very recently released. But what you can do is you can also take that distribution of inclusive all gamma gammas, and you can just bin it in terms of other variables like the PT of the gamma gamma system, and you can fit in each bin. You can now take into account for the fact that your measured value is not related to the reconstructed value, although this is reconstructed. And you can get a yield in each of those PT bins. And you find that there's a prediction, and here's the yields. It looks terrible. The official statistical value is that the probability of that is 39%, which is not very bad. I don't have a deep understanding of why this plot has a 39% probability, but it does. The n-jets distribution, where you do the same thing, you just take all gamma gammas, you divide it into 0, 1, 2, 3 jets, and you look at the distribution. It also has fairly large discrepancies. Apparently, generators vary a lot in their predictions of how many higher jet multiplicities you should get. And there's large statistical uncertainties. The paper doesn't even quote a p-value for this, but somehow dismisses this discrepancy as not being important. I can't add anything deep to that, except that I look at that and I really wonder how it's going to go in the future. I think you should be aware that after the end of the next run, these plots are going to have 10 times more data effectively. There's going to be 10 times more in those. So the error bars will be 1/3 the size that they are now, and you will actually really be able to probe out what these distributions look like. So if you have uses for those things, you should be thinking about them. Okay. Okay, so now I told you about the WW measurement. I told you a bit about gamma gamma. ZZ you can also subdivide into categories, but there's so few events in ZZ that you don't get a lot of information by doing that. And so what you end up with is a table of all the different categories that you've looked for signal in terms of the decay final state and the production mode. And here are all the categories where we have some sensitivity with little check marks. The sensitivities vary category to category. And what we do is we put these into a big fit. And one thing I really want to emphasize is that you cannot do this by reading the papers. You have to do this by contacting the authors and getting the table of all the systematics and all the bins and knowing the correlation between each bin and each other bin. There's some trivial things, like if I have a jet requirement in the gamma gamma analysis, because I have the 2-jet category in there, I want the uncertainty in that two-jet selection to be correlated correctly with the uncertainty on the two-jet selection in the WW analysis. If I don't do that correctly, I will get the wrong answer for my fit. I will underestimate the size of the uncertainties in general, because treating things as correlated, uncorrelated is not treating them as uncorrelated will underestimate the uncertainty. If I have two numbers that are 100% correlated, then the fractional uncertainty doesn't decrease when I combine them, right? But if I treat those uncertainties as uncorrelated, it will decrease. So I have to be careful about that. So to make this more, I added this, I forgot about that. To make that a little bit more strong statement, here's, I showed you this table before with all the different uncertainties for WW. This is actually a condensed table. The real table has about 100 entries, but we condensed this to make it readable in a paper, which means that, for instance, this line that says experimental objects in Drellon estimation, that's got like 40 or 50 different contributions. And when I combine this, say, with the gamma-gamma, the fact that our uncertainty on the electron ID efficiency for the WW will be correctly correlated with the electron ID efficiency in the 1 lepton plus 2 photon category in the gamma-gamma analysis. So that's a key piece of the thing. Also, all the theory uncertainties are correlated correctly. So, of course, every single thing that uses gluon fusion is going to have the same uncertainty here, and they have to be treated correlated. Every time I make a jet requirement, it's going to change the signal acceptance due to the jet requirement, things like that. And, of course, the integrated luminosity is highly correlated between all the experiments. Okay. So the first big combination you want to do when you put all these things together is, do we actually know that we're seeing VBF signal? And the answer is that right now, Atlas by itself gets 3.1 sigma. CMS is pretty similar of evidence for VBF production. So we're pretty sure we're seeing VBF production at this point. And what this is an error ellipse of how much overall Higgs we're producing via the gluon fusion and channel versus the VBF channel, and you can see the different contributions of each different measurement. You can see tau tau is completely consistent with 0, 0, but it's on the plot. Gamma gamma is this ellipse that I showed you before, the red one, so I already showed you that one. You can make a similar one for ZZ. You can see the size of the errors is quite large, and essentially no constraints in the VBF sector at all there, because there's just, you expect less than an event, so there's not a whole lot you can say. And then WW here is another error ellipse. I think that you can see the relative sensitivities of the measurements well here, that the error ellipse for the WW is significantly smaller than ZZ and comparable to gamma gamma, right? So that gives you a sense of the relative measurements and why I think it's worthwhile to spend so much effort on the WW measurement. So another thing about why is it important to see VBF production? Well, it's important because if you've only seen gluon fusion, then every single cross-section you measure, a branching fraction times cross-section, is proportional to the gluon fusion cross-section divided by the total width of the Higgs. So because when we measure something, if I measure the glue-glue production to gamma-gamma, I'm measuring glue-glue production times the decay rate to the width to gamma-gamma over the total width. If I've only measured things with glue-glue, then there's always a ratio of the total width to the glue-glue in there. So if I haven't seen VBF, I have no information about the ratio of those two guys, right? Or I have information only about the ratio and nothing about the absolute values of those two guys. Okay, so the next step is to go a little bit farther and actually try to extract coupling information. This is how I think the experiments would like to report the results. So although it's a little tricky, and I think this is something that needs to be worked out, it's an interplay between experiment and theory. We want to be able to probe, are there new physics in loops? Are there BSM contributions? So we want a very general theory that allows all those things to be possible. Right now, what we're doing is we're saying that there's one vector coupling that shows up here. There's one fermion coupling that shows up here, but it also shows up here in the top loop. And shows up, the vector, same vector guy shows up here in the Higgs decay, or in the W loop that contributes to gamma gamma, and the fermion one shows up in the top loop to gamma gamma. But there's already a bunch of options you can have here. You can either assume that you know what's in the loop, in which case I say, oh, I only need kf and kv, or I don't assume I know what's in the loop and I add a new parameter, k gamma, which is just the rate of the loop itself. And similarly for the gluon fusion diagram, I can assume I know what's in the loop and I say this thing is proportional to k fermion, or I say I don't know what's in there, it's proportional to k gluon, kappa gluon. So I already pointed out that this is what an individual measurement looks like. So then what we're doing is we're including in our fit the ratio of each measurement to its standard model expectation, and they're going to be proportional to a bunch of kappas, where we've added in one more kappa, which is for the total width. So we just say the total width is proportional to kappa squared, and that just makes our notation uniform, even though kappa h doesn't really have a physical interpretation. Okay, so the first fit that you can now do with this model is you can say, okay, let me assume that there are only standard model particles, no non-standard model particles, but maybe the coupling of the Higgs to these standard model particles is not what I think it is. So let me try to draw some error ellipse that describes how well I know that the coupling to the standard model particles is what I expected. And so, so I made this assumption. There's many different assumptions you can make, but I made that assumption, and I get a set of error ellipses here. Again, you get to see the relative importance of the different measurements. You see here the blue area is gamma gamma. The whatever color this is the 4 lepton, and the WW is the pinkish area here, and the red is the grand combination of all of them. You can see that this measurement allowed a relative sign flip between the fermion and boson couplings. So let me pause for a second and ask if anybody can look at this plot and tell me why ZZ and WW are symmetric and gamma gamma is asymmetric in that plot. Yeah? Sorry, repeat? Right. I think I'm having trouble hearing you, but I think you said that there's two diagrams there, and the two diagrams interfere, right? So these two diagrams in the gamma-gamma loop can interfere. So if I change the relative sign of this guy to this guy, I will change the actual rate, whereas if I change the sign here, it's just proportional to the square of the coupling constant, right? So it doesn't change. So you get these interesting effects, and we can in fact rule out at 68% but not 95% that there's a wrong sign in there. Come on, we probably know there's not a wrong sign in there, but we want to leave things open and agnostic. Another example of a fit that you can do is you can keep all the SM couplings fixed, but you can add BSM in the loops. So now I assume that I'm sort of at least in the decoupling limit where there's no major modifications to the Higgs to W, Higgs to Z, or Higgs to top couplings, but I might have some new physics running around in a loop, and I can actually constrain how off those loops are. And so I can do this with only standard model particles running around in the coupling and no non-standard model particles in the decay. And that gives me an uncertainty like this. You can see this graphically like this. This is the gluon loop, and this is the gamma loop. And you can see that it's in reasonable agreement with the standard model expectation at 1, 1. The reason that I then go and I say, well, what if I want to also allow an invisible decay or some other final state? I could have the Higgs decaying to some complicated two pseudoscalars that then decay to two taus that we just haven't seen yet. And so there's some other decay mode of the Higgs that I didn't know about, right? I can indirectly constrain that through these fits. I'm only indirectly constraining it with this funny assumption that they're standard model couplings, but I can indirectly constrain that. What you see immediately is that when I release the constraint on the total width, then what I get is a less constraint on the gluon fusion loop, right? And this is just because of my point, if we go back, that this ratio is only constrained. That now, if I allow this guy to change, if I have most of the information from the gluon fusion, then this ratio, I know this ratio, but I don't know each individual component. If I keep this guy fixed, then I have a pretty strong constraint on the top guy, because that's just the constraint on the ratio. But if I allow this guy to vary, then I have much less constraint on the top guy because it's the ratio that I really measured in most of my measurements. Okay? And so the other thing I can do then is if I've released this constraint, I can get a limit on how much non-standard model stuff the Higgs is decaying into. And it's at about the 60% level. So I know that the rate at which Higgs decays to non-standard model is less than about 60%. But, and it's always important, because you see these numbers out there in various theory papers, lots of people have done this fit. It's important, one, that the fit be done right. It's also important to keep in mind what the assumptions are. Right? The assumptions are that the standard model couplings are fixed. If you also allow me to change the W and Z and top couplings at the same time as I'm changing these loops, I can probably get farther away from this. I can probably allow more in there. Okay, so the last thing I wanted to talk about is that I just showed you this indirect limit on how much the Higgs is decaying to non-standard model stuff. We've also done a search where we looked at directly for the Higgs decaying to invisible particles. So this goes through a diagram that looks like this, where I have QQ bar goes to ZH, and the H goes to invisible stuff, and the Z goes to leptons. And so what I do is I just look for 2 leptons, make a Z mass, recoiling against nothing. So Z goes one way, nothing goes the other way. I say, oh, there's invisible stuff. Of course, there's a big standard model background, which is I just get 2 Z production, where one Z goes to neutrinos going one way, the other way I get 2 leptons. I really can't do a whole lot about this guy except for model it, right? So this is another place where theory comes in. I have to know this cross-section well. And in fact, in order to select these events effectively, again, I had to make a jet veto. So again, I made this jet veto, which introduced another uncertainty. Now I don't have a great control region anymore, so I can't use a control region. And so in fact, in the end, our limit is we're just about to the point where we're dominated by the uncertainty on that guy. It's again a case where this guy is about half the uncertainty. The normalization of that guy in statistics is about half the uncertainty. If we want to go farther, we have to be able to normalize this guy better in some other way. And so what we end up with is a limit that just sort of coincidentally is close to the one that we get from the indirect fits. Of course, the fits had various assumptions. This guy has no assumptions except that the Higgs decays to invisible. And so this is the limit on the Higgs decaying to invisible. It's slightly better than the expected because we have a deficit of events. So this is the missing energy distribution in these LL plus nothing events. And this is the solid line is what the signal would look like. I think that's a 100% branching fraction to invisible in the solid line. And so you can see that 100% is excluded. But if I scale this down by 2/3, it wouldn't be completely excluded. So that's where we're at. And then it's the normalization of the green area, which is the ZZ, which is the main limiting factor. Okay, so why is that interesting? So this is a plot that was made several years ago. We have an internal version of this plot, which is not public yet, but I wish I could show you. But it looks essentially identical because people fairly well estimated the sensitivity of this invisible search before they even knew that the Higgs existed or what its mass was. So this plot has a bunch of different predictions. The one that's most applicable here is the ZH to invisible predicted sensitivity at MH120. The collider energy was different than this estimation. The luminosity was different than the estimation. The Higgs mass is different than the estimation. But in the end, it turns out that the expected sensitivity that they had was very close to what we have now. So we have a limit that looks like this blue line. And the interesting thing is if you look at this blue line and you look, this is the WIMP nucleon cross-section versus WIMP mass. And here are all these famous possible signals that you've heard about from Neil. He drew this plot on the board. Here's the plot itself. There's one thing missing from this plot because it's an old plot, which is that the CDMS signal is somewhere over here. And so if you start to say, well, these guys, if you add these up and you say, oh, well, maybe I'm beginning to believe this thing, what this plot is telling you is if these guys are real signals, they are not coupling to the nucleon via a Higgs. It's just excluded, right? This blue line clearly excludes all of this. So by a lot. So that's a very interesting constraint and a note of what we might be able to do in the future. Unfortunately, you can't actually see anything that's past half the Higgs mass. Your sensitivity drops dramatically. This is only really possible because you're getting a resonant enhancement in the nucleon collision to dark matter via from the Higgs resonance. So if you're not going through the resonant part of the Higgs, you're not getting that enhancement, and your sensitivity is terrible. Okay, so here's the summary, that there's this important interplay between the theory and the experiment. So I talked for the first part about how there's a lot of theory input into the Higgs to WW measurement, and it's really important that we understand how to optimize that interaction, because otherwise the WW measurement and other similar measurements where we look for new physics in broad distributions are going to hit brick walls. Experiment is an important input into theory. You have to do it carefully, including all the systematics. That was sort of the second part of what I talked about, where you take all these measurements and you combine them and you get coupling constraints. I think those coupling constraints are where we want to meet, because those things have fairly well-defined values and there's a fairly small number of them. Whereas if we try to meet at the pure experiment number, then you need to know what the correlations are between all the measurements, which involves all sorts of details of the detector response that you probably don't want to know about. And so I think I also already said this, that the measurements are close to being theory limited at this point. To set a scale of where we're at now, we have about constraints on these couplings that are at the 20 to 30% level now. We're just sort of crossing the sensitivity to actually seeing the fermions, but it's not clear. We're going to have a hiatus. There's not going to be a whole lot of progress for the next 2 years. And then I think within a year or so, we'll know pretty well whether the Higgs is coupling to fermions and at least get the right order of magnitude on the production rates over the Yukawa couplings. We have a lot of interesting sensitivity to dark matter via the Higgs. There are these Higgs Portal models, which were very popular until they're now excluded, essentially. Although you can resurrect them in various ways, which I'm sure you know better than me. And then I didn't mention, basically because I wasn't surprised by the result, that the thing that we found is spin 0 plus. Various combinations of 0 minus, 1 plus, 1 minus, and 2 plus have all been excluded. I think you can get an admixture of 0 minus and 0 plus, which would never be completely excluded because you always make the admixture smaller and smaller, but otherwise these things are out. And so that's where we're at. Okay, any questions? Yeah.
I saw the slide where you have this plot where you compare the India cross-section to the New Orleans cross-section.
Mm-hmm.
There's this flat region, the contour plot. No, slide 43.
43.
Yes.
Right.
The contour for ZZ is sort of flat. Can you explain about that?
Ooh, that's a good question. So what does that mean? So the thing with ZZ is that you can run out of sensitivity where you just don't expect or see any events. And I suspect that that's what that region must correspond to, that if you don't expect or see any events, then you don't get much of a limit. But this would imply that I cannot put something right here. Yeah, sorry, I don't have a good off the top of my head of why that is, that it has a funny flat boundary. It does look a little suspicious. Usually you get features like that when the model doesn't make sense anymore, but I don't know why. I can't think off the top of my head of why that doesn't make sense. Any other questions? Yeah. Okay, so the question is whether long-term the indirect method of doing the fit here, whether this fit will give a better constraint on invisible, or whether direct measurement will give a better constraint on invisible. In the long term, I think the answer, there's two things that I would say. One is that it's important to note that this is a model-dependent statement. It assumes this. If I get rid of that, I think I can basically have any invisible I want, right? But with these assumptions, then the next answer is that eventually you're going to end up hitting the theory wall due to the gluon fusion cross-section uncertainty, and that's going to cause trouble. Experimentally, I think that we'll be able to be clever enough with this measurement and a related measurement with VBF production where you have a Higgs decay to invisible, where if we can effectively normalize this guy using data-driven techniques or combinations of theory and data-driven techniques, statistically there's no limit really. It's going to keep getting better for a long way. We're talking about having something like 1,000 times more statistics over the next 15 years. So my guess is that we're going to end in the 10% range of sensitivity before it really gets hard. Okay. Yep.
Yeah, somewhat related. How fast do you think you can, how fast will this 50% statistical uncertainty go down with the next run? I don't know.
The 50%.
Well, you're claiming you have 50% statistical uncertainty more or less in inclusive cross-section, something like that. At the very beginning, when you were talking about statistically versus systematic uncertainties.
Right. So for the WW, it's 20% right now. And so what I was saying, I think maybe you got misinterpreted, was that there's a 20% systematic and a 20% statistics right now, so the uncertainty is 50-50. The statistical one is going to go down by square root of 10, roughly. And then the systematic one, I just don't know where it's going to go, right? We have to be more clever. It's going to hit a brick wall. Some of it will go down with data, but a lot of it won't go down with data. So you also have to think that some of these things I can get rid of by ratios. So I could measure the gamma-gamma rate with 0 jets and the WW rate with 0 jets. And if I make the ratio of them, then I cancel out the uncertainty from the gluon fusion inclusive production. I also cancel out the ratio, the effect of the acceptance from the jet vetoes. So the combination of those should allow me to get a much more precise measurement of, for instance, gamma-gamma over WW than I might be able to do of WW by itself.
Okay, but just the statistical one, the next run will be no topic anymore.
So just this.
After the next run, after your C turns on again.
Right.
Collect more data, the statistical uncertainty will be no topic anymore. How large is it after?
So the statistical uncertainty on WW will be about 7% by the end of the next run. And if you count all the way out in runs, it's much smaller, right? You have to divide by a square root of 30 of that. So it's getting quite small. I don't think we'll ever be able to make use of all the statistics we get with that kind of I don't think we'll ever be able to make use of all the statistics, the 3,000 inverse femtobarns, for the gluon fusion analysis. But for the VBF analysis, if I extrapolate this kind of plot for VBF to 3,000 inverse femtobarns of 14 TeV data, and I think about making slightly tighter cuts, I think I can probably get to about a 5% measurement of that process, and it has a small theoretical uncertainty. So that I think is a really interesting possibility because it begins to get you into a precision range where you might have sensitivity to, sensitivity to things like the width being off by relatively small factors or the WW coupling being off by relatively small factors. Of course, also this production rate is proportional, this process, the VBF version of the process, I don't have the VBF diagram here, the signal here is proportional to the HWW coupling to the fourth. So if you get 5 or 6% on the VBF to H to WW, you're getting close to 1% or less than 2% on the single coupling. Other questions? Okay, so I guess we can go ahead and go to lunch.